Welcome to the HyperX Academy. This video will provide an overview of hyperloads, affectionately called Space Potato, which is the new loads enveloping feature available in version 2026.1. Aerospace structural design is fundamentally guided by this equation. For a structure's computed design to loads, coming from FEA, HyperX performs sizing by ensuring that the allowable load, based on prescribed failure criteria, is greater for each zone by finding the lightest weight design that attains positive margins of safety. Hyperloads is a visual tool for you to verify and fully inspect results from all three parts of the equation in 3D space. We'll start with the design to loads part of the equation. As an example, let's look at the Collier Aerospace UAM wing model provided with the install, which represents a generic wing you might see in the urban air mobility industry. As a stress analyst, the first thing you will want to quantify about a model are loads. As you can see in HyperX or in a preprocessor, you can plot the element-by-element forces directly on your model. You can toggle between load cases and individual components of load as needed. You do this to try to understand what load cases are critical for which parts of structure, what components of NX, NY, and XY load are critical, looking for hotspots in the magnitude and the distribution of load across the skin. Interpreting element forces load case by load case, load component by load component for each zone is cumbersome to keep track of in this way. And while possible, it doesn't help identifying the highest combination of NX, NY, and XY load. Let's look at two different panels in different locations on the wing. For each panel, you can make a scatter of points to represent these loads in 2D space. Here, each point is a load component for a single element, for a single load case. On the left is a projection of points on the XY plane, middle the XXY, and right YXY. You can use these plots to see, for example, that the root panel is dominated by compression NX, while the panel located near the engine pylon experiences more severe multi-axial loading. A 2D convex hull can be drawn around the extents of these points, creating 2D envelopes in each plane. But even more useful is to combine these three 2D views into one 3D surface envelope. This is where hyperloads comes in. By selecting these two panels and opening the hyperloads viewport, you can see the same scatters for each of these three planes. Then, by viewing the 3D envelope, the engineer has a way to inspect the load magnitude combinations of NX, NY, and XY in one plot, for every element for every load case. In particular, note how the root purple panel is dominated by compression NX, and its resulting envelope in the XY plane is cigar-shaped, whereas the middle zone has loading from the engine that causes multi-axial forces of all three NX, NY, and NXY. Viewing cases like this in 3D space is important because the critical load is not captured in 2D envelope plots. You can also use the hyperloads interface to view the element loads as a scatter plot in 3D space, bounded by the convex hull. We'll focus on the panel closest to the engine pylon and adjust the plot settings. Now, each point represents the load for one element for one load case. There are 154 elements in this zone and 17 load cases, making a total of 2,618 points, colored by load case. You can also use this view to understand which element load case combinations bound the convex hull, or make up the skin of the potato. The load scenarios that form the envelope are critical, and therefore are the ones that should be used for sizing. Now we'll consider the allowable load. Each panel bay on this upper skin, identified based on the rib and spar, is modeled with a FEM property, such as P-shell or P-comp. The amount of load a panel design can sustain, or the allowable, depends on the structural concept chosen for that panel. HyperX optimizes the structural concepts per panel during sizing. For the root panel, which we saw was compression dominated, let's consider a hat stiffened panel. The dimensions for this panel have been sized by HyperX using only max strain in the 1 criterion. Both the skin and the web of the hat panel were sized as composite laminates. For the other panel, which had a lot of multi-axial loading, for illustrative purposes, we'll consider a metal plate. The thickness of this plate has been sized by HyperX with respect to the familiar von Mises criterion. Just like with the design 2 loads, Hyperloads is able to generate 3 2D allowable envelope planes based on each design and corresponding failure mode. Combining these 3 planar views into one 3D surface envelope provides the engineer a way to inspect the allowable combinations of NX, NY, and XY in one plot. This is done per panel design, per all-included failure criterion. It also takes into account all objects and object-specific failure. You can see the familiar egg shape of the von Mises envelope for the metal plate, and the higher axial strength capability of the hat panel. Let's look at a more realistic case. The panel closer to the wingtip has been sized as a hat with a soft, quasi-isotropic laminate. Several different failure criteria were considered. By plotting the allowable load envelope in hyperloads, and then coloring by criterion, you can understand which regimes of the envelope were controlled by which method. You can also color the envelope by object to understand which object in the hat panel was the driver for each surface of the allowable envelope. Now let's talk about the margin of safety. Let's look at the metal plate. In the Hyperloads interface, we can overlay both the design 2 and allowable load envelopes in the same plot. If the allowable envelope completely contains the design 2 loads envelope, the design will satisfy all load cases, and therefore has a positive margin of safety. Here, the design 2 loads envelope is shown in teal, and the allowable envelope is shown in blue. In these 2D views, we see that the allowable envelope clearly contains the design 2 envelope in each plane. But when we inspect the 3D plot, we can see that these surfaces actually get much closer to one another than the 2D plots would have led us to believe. Plotting the critical margin vector confirms this. As you can see, HyperX has optimized the sheet thickness to be as thin as possible, while still having margin of safety greater than 0. In this case, though, the panel was more dominated by interaction of load components, which is better captured in 3D. Point being, in many cases, the critical load surface and analysis failure surface is not able to be seen in any of the 2D envelopes, as it is truly a combination of all 3 load components.